Alright, good afternoon. This should be for my period 4 or period 6 class on Wednesday. Today's key topic is linear functions. Linear functions is about knowing what equations, tables, or graphs create lines. So linear functions is about knowing what equations, tables, or graphs create lines. Alright, so if we go to your first column here, we have equations. Before we do this equations, just a really quick teaching moment, I guess. If we have a function that looks like this, it says f of x equals 2x plus 1. That's not a way of writing y equals 2x plus 1. This on the top, this is called the function notation. And so what we do with this, one way we read it is we say like f of 1 equals, and that just means that you're going to put in 1. So 1 times 2 is 2, plus 1 would be 3. So f of 1 is 3, f of 2 is, well, 2 times 2 is 4, plus 1 is 5. So that's just another way of function notation. And we use other things than just f. So if we have two functions that are the same problem, you could use g or h or any of those variables. It's just a way of saying that those are the functions. When you plug in 1, we get 3. When you plug in 2, you get 5. So that's function notation. So it's just f of x equals, and then it says the function over here. It's kind of the same idea as having a y. Very similar. Alright, so with your equations, you know an equation results in a line if it ends up with, if you can write it as f of x, or that function notation, f of x equals mx plus b, or y equals mx plus b. This is an equation that you'll get really familiar with by the end of the year. It's called slope-intercept. And what this is that m is a number here, and b is a number, a different number, or it could be the same number. So you're taking a number times x, and you're adding another number. So here is your variable part, your variable term. M is the coefficient. B is your constant. Alright, so if we are looking at some examples to tell if they're linear, or we say non-linear, so if they don't create a line. One example would be f of x equals the square root of 6x. Notice that the x is underneath the square root. In our function notation that creates a linear function, the x has to be by itself. It can't have exponents or be under a square root. So this is nonlinear. Okay. Our next one we have is y equals negative 3/4 x plus 7. Notice we have a coefficient, it's negative 3/4. That's a number, it's a number times x, and we have a constant. The constant is 7. So in this example, this is linear. Okay. Our next one that we have is, getting there, sorry, y minus 4 equals 3 times the quantity of x plus 2. Now this problem right off the bat, we can't decide because the y isn't by itself. To know it's linear, it has to be y equals. So you have to get rid of that subtracting. But also, in this y equals mx plus b, there's no parentheses. So if we can get rid of the parentheses, we want to. So here, we want to get rid of the parentheses by doing our distributive property. Pew! Pew! So we get y minus 4 equals 3 times x, which is 3x, plus 3 times 2, which is 6. Now we want to get rid of that subtracting 4, so I'll draw my line down the middle. I add 4 to both sides. Whoops. Alright. That cancels out the minus 4, so I get y equals 3x plus 6 plus 4 is 10. Now this is our final in function form. This is called function form when we get the mx plus b. Because it has a coefficient of 3 and it has a constant of 10, it is a linear function. So we can say that's linear. A couple more examples here. I think we have 2 more. Our next example is y equals 4. Notice in this example we don't have, 4 is a constant. So that would be our green, or our B. I'm highlighting it in green. So that's a constant. So can we write it with an mx? Well, actually we can. This is the same thing as writing y equals 0x plus 4. Where the 0 is the coefficient. So this is linear. It does create a line. Alright, last example here. We have, sorry, I gotta extend the page here. Y equals 5 over x plus 2. In this problem, you can think of 5 kind of as the constant, or as the coefficient. But the adding 2, this is definitely the constant. There's no variable there. But if we moved that out front, it'd be y equals 5. And then this is still 1 over x plus 2. Since this isn't just an x, it's a 1 divided by x, anytime the x is in the denominator, it makes it nonlinear, which means it doesn't form a line. Okay, so those are our examples. I gave you a couple that are linear, a couple that are nonlinear. Alright, here we go to tables. Alright, so we're in that middle column. For your tables, there has to be a constant increase or a constant decrease in your x's and y's. In your x and y values. Okay, so there has to be constant increase or decrease in x and y values. Alright, so here's our first table. In these tables, unlike yesterday, well, one way to make a table is you can have x on top, y, and then have your values. The tables we're going to do today are called t-tables. So we have an x and a y. Alright, when I call these out, they're pairings. You're going to have 3 tables here, so but even those out. For your first pair, you have 6, 3. Then we have 8, 1. Then we have 10, negative 1. 12, negative 3. Okay, so when we do this, we're looking at the x's and how they increase with the y's. So in the x, we're adding 2 here. On the x's, we add 2 to go up. On the y's, we subtract 2. On the x, from 8 to 10, you add 2. On the y's, from 1 to negative 1, we subtract 2. On the x's, we add 2. And on the y's, we subtract 2. So since every time we add 2 to the x, we subtract 2 to the y, we add 2 to the x, we subtract 2 to the y, we add 2 to the x, we subtract 2 to the y. That creates a linear function. so it's linear. Sorry, my pen kind of freaked out there. Alright, we have two more tables here. Our next table for our, well, I guess I'll split mine in half here because I don't have enough room. So we have x, y, we're making our t table. And actually we don't have to make a line in between every one, we just have to make sure they're separate from each other. So we have 1, 2, 2, 4, 3, 8, and then 4 and 16. Okay, so for this problem, when we look at our x's, we're adding 1 every time. So to go from 1 to 2, we add 1 at each time. So since this is constant on the x's, we want to make sure we're constantly doing something on the y's. To go from 2 to 4, we add 2, but to go from 4 to 8, we add 4, and to go from 8 to 16, we add 8. So since every time we add 1 on the x, we're not adding the same thing on the y. It's not add 1, add 2, add 1, add 2. It's add 1, add 2, add 1, add 4, add 1, add 8. Since those aren't the same, this is nonlinear. Okay, it has to be constant between the two. Alright, we go to our last example. Our last example, we have a t table, x, y. My lines are very crooked today, I apologize. Alright, so for our x's we have 0, 27, 1, 9, 2, -3, and 3, 1. 0, 27, 1, 9, 2, -3, 3, 1. So on the x's, every time we're adding 1. So to go from 1 to 2 is add 1, 2 to 3, add 1. Okay, on the other side, we have to remember we're either adding or subtracting. So here we're subtracting. And 27 minus 9 is 18? 18, I think. So we subtract 18. To go from 9 to -3, we're subtracting, oops, sorry, that was supposed to be +3. I apologize. That's a +3. We subtract 6. And to go from 3 to 1, we subtract 2. So since it's not add 1, subtract 18, add 1, subtract 18, add 1, subtract 18, it's switching over here. When these are staying the same, it's nonlinear. Alright, so it has to look the same. So in this first example, it's linear because it's add 2, subtract 2, add 2, subtract 2, add 2, subtract 2. If it would have done this, 6, 7, 8, 10, with 3, 2, 1, -1, we want to see that even though this is add 1, subtract 1, and then add 1, subtract 1, even though here it adds 2, that's okay as long as this doubles on the other side. If it doubles on the x, it has to double on the y. So it has to be -2. Okay, so as long as it has that constant rate on the left, constant rate on the right, it works. Alright, I have one last column. Whoops. Alright, your graphs are pretty self-explanatory. I mean, if it's linear if it creates one straight line. It has one straight line. Pretty simple. Okay, you're going to create 3 graphs here. I'm running out of time on my time limit here, so I'm going to pause it and do it. Okay, so for your first graph here, what this is going to look like, so if we have kind of a V going, I'm going to make that a different color, how about? Is kind of if we have a V going here, like this. Is that linear? Well, technically it makes 2 lines, but it's not one straight line, so this is non-linear. Okay? Another type of graph that we're going to be able to see more so in the future as we keep going here is something that looks like this. Okay, is that linear? Again, that's pretty self-explanatory. It doesn't create a line, so that's non-linear.